Okay, so we've got a video today about complex numbers and conjugate roots. We've mentioned complex numbers before when we did our quadratic unit, so some of this will be a review for us. I feel like some of us need some more practice with it, which is why I'm bringing it up again. So you could potentially fast forward through a lot of this video if you see that a lot of it is familiar. But I am going to relate it to polynomials and why it's important to us with polynomials with a higher degree other than 2. So mostly a review, but we will get more practice with it because I do feel like we need more practice before the park. First, I want to recall some properties of a complex number system. So remember that the complex number system contains all real numbers. So any real number can technically be written as a complex number, where the coefficient of the I term could just be 0. So for example, I could have 2 plus 0i, which is really just 2, but it's technically complex. So keep that in mind. Number 2, the addition, subtraction, multiplication, and division of complex numbers obey the same rules that the real numbers do. So keep that in mind as we're working through our problems on Tuesday. The complex number system contains a number denoted I, such that I squared is equal to -1. Sorry, I can't talk. So we've learned this before, nothing new. Every complex number can be written in standard form. We've already discussed this. The important thing, I guess, for today's lesson is this part right here. We are learning that we can solve for variables knowing that if we have a complex number a plus bi and it's equal to another complex number c plus di, we know for a fact that a must equal c and b must equal d. And we're going to talk about that in our first example coming up. So overall in this lesson, we should be able to answer our essential question, which is what can I conclude if I obtain a solution to a polynomial in the form a plus bi. So if I end up with a solution that looks like this, what does that mean? How can that help me, etc. So going on to our first example, equating two complex numbers. So this will be something that you will see on the park. I've seen a couple questions like this on the released items or on the practice tests that are online. So make sure that you are able to recognize this and that you're able to solve this. It's a very easy process. So we discussed on the previous slide that a plus bi, if I have a plus bi, that's going to equal, or that could equal, c plus di. If this is the case, I know that a must equal c and then b must equal d in order for this statement to be true. So I'm going to apply that to this statement here. In this case, my real number, my real component is the 2x, so my 2x is really my a value. And then looking over at this side, my c is -6, so all I have to do is set up this equation, divide by 2 on both sides, and I've got my x value is -3. Easy enough. I think the hardest part is probably recognizing it, and it could be tricky because I technically have two different expressions, but both of them don't contain x and y. So usually people try to set it up as a system of equations, but that doesn't work in this case. So be careful with recognizing some of these. The next thing would be b equals d. In this case, the b is the coefficient of the I, so it's the real part of the imaginary component. So it is a -3 in this case. And then the d is the 4y. So the 4y together make up the coefficient of the I. So then, again, easy enough. I just divide by 4 on both sides. So I have -3/4 is equal to y. So done with that example. And you will have a couple like this on your worksheet for Tuesday. If you have questions, let me know in class. Example number 2, adding, subtracting, multiplying, and dividing. Should be pretty simple. So if I take part A, we know that the properties are similar to what we've learned with real numbers. So if I'm adding 1 plus I to 3 minus 7i, all I have to do is combine the real components to each other. So I have 1, and I'm just going to rewrite the way that this whole thing is without the parentheses. I have 1 plus I. If I distribute it that positive, I still have a +3 and then a -7i. So all I have to do here is combine like terms. So I know that this and this are both the real parts, so I would have 4 here. And then I know that this and this are both of my imaginary components, so I minus 7i would give me a -6i. So this would be my answer for part A. You can think of the I as almost like a variable, so x or y or z, so you can only combine like terms, so be careful with that. B, on the other hand, we're subtracting now, so I would have to distribute this negative to both of these terms. So I would have the 4 plus 3i, and then now I have negative 8, and then a positive 6i. So again, combining the real components, I have 4 minus 8, which gives me a negative 4. And then I have 3i plus 6i, so I'd have 9i. Easy enough. Part C, when I'm multiplying, I'm going to have to distribute this term. So the 4i times the 2 gives me 8i. If I distribute it to the next term, I have a positive in the middle, 4 halves, and then I have an I squared. So this is where I have to kind of simplify it a little bit more. So this first term I cannot simplify anymore, so I leave it as 8i. This I know goes down to a 2i squared, but recall that I squared is the same as saying negative 1, so I have 8i plus 2 times negative 1. Simplifying that further, I have 8i minus 2, so that would be my final answer for this. So make sure that you are simplifying as much as you possibly can. And then going on to part D, this is where I have to use the FOIL method or the distributive method, however you want to think of it. So multiply these two terms first, so I have 6 here, and then I multiply the outer terms, so I have negative 8i. Then I distribute the second term, so positive 3i, and then this next one, minus 4, and then I have I times I, which is I squared. So now combining like terms, I can't combine anything with the 6 for right now. These two, though, I can combine, so negative 8 plus 3 is a negative 5i. And then this I can rewrite as negative 4 times negative 1, because we know I squared is negative 1. So now I can actually combine something else with that 6. So this becomes a positive 4. So 6 plus 4 would give me 10 minus 5i. So that would be my answer to that one. So typically you'll notice this pattern where we have them always with a plus bi, and so on. This one I guess I could have switched around, but we get the idea. That's the simplest way to write a complex number. So these operations shouldn't be anything new, and they shouldn't be anything that's very difficult for you guys. You will get more practice with it on Tuesday. This is where we get into the polynomials and how it relates to what we're doing now. So I want to find all of the solutions of I cubed is equal to 1. So remember that solutions are when I have my polynomials set equal to 0. So if I start with x cubed equals 1, I want to subtract the 1 from both sides. So I really have x cubed minus 1 is equal to 0. So now I can start to solve it or factor it. Recognize that this is a difference of cubes, so I'm going to factor it the way that we learned how to factor difference of cubes. So I have x minus 1, so keep the same sign for the first parentheses. The next one I'm going to do x squared. You square whatever this first term is. Different sign, so I'm going to add. And then the a times the b, if you recall, so this is really just x. And then this one is always positive, and then it's this term squared, which just ends up being 1. So this is my difference of cubes, and it equals 0 still. So I know that these are my two factors of my polynomial, so in order to solve them, I need to set each of these sets of parentheses equal to 0. So I can start by saying x minus 1 equals 0, which tells me that x is going to equal 1 by adding 1 to both sides. So there is one of my solutions. Going to the next one, though, I'm going to use quadratic formula because this one is actually not factorable anymore. So looking at this, I know that my quadratic formula is x equals negative b plus or minus square root b squared minus 4ac all over 2a. So then my b term is 1. So I've got a negative 1 plus or minus square root of 1 squared minus 4 times a, which is 1, c, which is also 1, lots of 1's in this one, which makes it nice, and then 2 times a, which is 1. So here I've got a negative 1 plus or minus the square root. This becomes 1 minus 4, over 2. So then I've got -1 plus or minus square root of -3 all over 2. So then this I know I'm going to end up with an imaginary number because I have a negative in my square root. So I have -1 plus or minus I root 3 over 2. If I want to separate this into my actual two solutions, so all of this is my x's, so x equals this, I could separate it. So one of them would be -1 plus square root of 3, I root 3 over 2. I'm actually going to separate this into two separate fractions, so I really have a -1/2 plus the square root of 3 over 2, and then the I next to it. So you'll notice now this is in the form of a plus bi. So we typically want to get used to writing it in this form. Going on to the next one, I did the positive version, so I want to do the negative version of it. So I have -1 minus I root 3 over 2. So again, writing it in two fractions, I have -1/2 minus square root of 3 over 2i. So all of my solutions are these ones here. We've talked about how we could possibly get imaginary solutions even with cubic and quartic functions. So here we've got this. One thing I want you guys to note is that both of these terms are conjugates of each other. So these are a conjugate pair. We might have recalled hearing this during our quadratic unit, but maybe some of the groups didn't say it. So a conjugate pair is basically when you have the same binomial, but the only difference is that this middle sign is different. So this one's a plus and this is a minus. This conjugate pair is really important, especially when you get onto calculus. You have to be able to know that these, when you multiply them out, will get rid of that middle term that you have. So conjugate pairs are really important, and conjugate pairs especially relate to difference of squares. So if we recall, a difference of squares is something like x plus 1 and x minus 1. You'll notice that if we multiply those out, we get x squared minus 1, so that middle term with just the x goes away. That's what's important about a conjugate pair. So keep that in mind. Conjugate pairs with imaginary numbers especially are important because they can get rid of some imaginary components, as we'll see in some examples. So keep in mind what a conjugate pair is. So these are all of the different roots of my polynomial. Going on to our next example, a conjugate root theorem. Actually, sorry, not an example, but an example will follow this. So a conjugate root theorem is important because it tells you that if you do have something in the form of a plus bi as a solution, then you know that the conjugate is also going to be a solution. So if somehow you know that this is a root, you know by default that this other conjugate will also be a root. So it's important to note that just in case you ever get one, you know by default you have the other one as well. So important theorem to know or to keep in mind when you're factoring. So the last example that I have for you guys is something that we will be practicing in class a little bit. So make sure that you know what a conjugate is, and then we can use those when we have something like this. So this is not rationalized, and it's because I is the square root of -1, so I know I can't have a square root in my denominator. So I want to rewrite this in a way where it is in the form a plus bi. So that's my goal here. What I want to do first is start by distributing both of these terms. So I have 4i in the denominator, and then this becomes positive 5i squared. And then the numerator stays 1. So I know that I squared is the same as saying -1, so I have 4i plus 5 times -1. So looking at this, really my fraction comes down to being 4i minus 5. So I want to take this and I want to multiply it by its conjugate, because by multiplying by the conjugate I will get rid of the imaginary term at the denominator. So the conjugate of this would be 4i plus 5. So same exact binomial, just a plus instead of a minus. And then I have the same thing up here, so 4i plus 5. Remember that you want the same thing in the numerator and the denominator because something divided by itself is just equal to 1. So I don't want to change the value of this, I just want to change its appearance. It's always the way that I remember it. So the numerator now becomes 4i plus 5. The denominator, though, I have to distribute to solve. So the first two terms, 4i times 4i, becomes 16i squared. Then I distribute to the next term, which is a positive 20i. Distribute the second term, so I have a negative 20i, which is now how I can see that those i's cancel each other out. And then negative 5 times positive 5 is negative 25. So 4i plus 5 in my numerator. Denominator becomes 16 times I squared, which is negative 1. These two terms cancel each other out because positive and negative, opposites of each other, and then we've got the negative 25 down in the denominator. So 4i plus 5 all over negative 16 minus 25. So here negative 16 minus 25 becomes negative 41. And then I still have the 4i plus 5 in my numerator. I do want to separate this, though, to become something like this standard form. Keep in mind you can only separate fractions like this when you have one single term in the denominator. So if I had something like this fraction up here, I wouldn't be able to split it up into two fractions. So be careful with those properties of fractions. So here I could separate this to be a negative 4i over 41 plus 5 over negative 41. I am going to rewrite this, though, so that it's in this form exactly. So technically I have a negative 5 over 41 minus the 4 over 41, and then the I component next to it. So this would be the proper standard way to write this imaginary number. So that's it for the notes today. I will see you guys on Tuesday, where we will have more practice with operations that involve complex numbers and conjugates. So conjugate pairs, and then you'll see a couple with the conjugate roots when you are factoring. So we've focused on real numbers so far. Now we're getting into the imaginary numbers, and then we're pretty much done with this unit. So we'll have another week or so left on this. We will likely take an exam and then start on our next unit with rational functions. So have a good long weekend, and I will see you guys first thing on Tuesday.